Hello there. Welcome to another problem session. So today we are going to do a circuit. So this is goes by the name RL circuit. Every circuit, whether you have something with a self-inductance, like it looks like some kind of solenoid here, but it doesn't have to be a solenoid. You know, like this circuit, say if I draw a circuit, like this, and suppose I have a current and there is a switch, maybe switch on the negative side of the current, switch here. If you turn it on and the current starts to flow, the current is changing with time, and so its magnetic field, if the current is going this way, magnetic field is over here and over here. The magnetic fields are, so you can see the magnetic field flux through there, d phi bt, with this surface S, dt is not zero, hence the current, it will induce a EMF and induce some current inside there. This back EMF, back current goes by those names. So this is the voltage that you set in, but in addition you are going to get inside here is going to be an EMF induced, and this induced EMF, to take into account, you can say, well, the circuit has some inductor, so you can say what's the EMF induced? So a d phi b dt, that's equal to L times di dt in the circuit. So you can to take that if this is going up, the current is going to go in the opposite direction, and so you just put a minus sign here, minus L di dt. Okay, so this is the physics origin of it. So here you can have any circuit, but here this part, you can say, what when you write something like that, is this part is considered all the self-inductance part of the circuit is put together in one block. So this one, you'll say when current goes through this, there is no R, this part R, and the entire circuit has some kind of resistance. So this part, we're going to say L is 0. So this is like this is when you draw a diagram like that, you're writing individual elements separately, right? So so this is a circuit that originally was there. Let me write that down. So it was this way, and the current was going on, and it was not connected. So that was the circuit, you might say, before, right? So when you can say this is not there at t equal to 0, and for a long time this thing has been going on, and a final some current level has reached. If you studied before, you probably know that the situation has been like this, right? Situation has been so t equal to 0. So say over there is t equal to 0, over here is t equal to 0, and so this is t equals to minus infinity. So of course you're not going to reach, so it's kind of reached some final level. Okay, so this is the I max. Now this one has no R equal to 0, and this I max, supposedly I max and at that point di dt equal to 0. So when it's reached, there is no self-inductance. So there's no self-inductance. So at that time, everything is dropping over here. Okay. So Imax will be just like to get an Imax. To get an Imax, you can think of the circuit is just being so this just R and this V. So if I give you this circuit, I mean this is V is that way in diagram. So if I give you this, then answer for A will very simple for you. This is just V equals IR. So the answer for this part of problem is very good. Imax is simply V over R in this circuit. So that's the answer for A. Okay, how do you do B? Let me pause it. And okay, so how do you do B? Now the circuit is actually this. And the current is also, this is a new current. So basically what happened is I had a circuit and it was connected for a long time, and then I have a way to skip this. So there was another wire, you might say another wire from here down here. So and then let me put it over here. So another wire was like this, and then this was from minus infinity to 0 time, and at time time 0 this thing was over here, and then connects that guy at t equal to 0. So now what will happen is there's no battery anymore. It's just like that. So the current was at t equal to 0 was I max at t equal to 0, and then at some other time this will be I of t at t greater than 0. So there's nothing there, but because this is di dt is not 0, you're going to have EMF which will be equal to L di dt. There's an L for the circuit. You can assign what the EMF was, and the EMF was basically B dot n hat dA ddt. So that's the EMF from the Faraday law. And the reason you're going to have is the same reason, because now it is changing. Then if the current is this way and is decreasing, of course you have if you use right hand rule, so it's going to be magnetic fields would be this way inside, and outside magnetic field outside like this, and all around. So this is the area in which magnetic field changing, and so magnetic flux is changing, and so that's what the EMF is induced by the Faraday law. So and just before I explained earlier, you have an L for one way to write Faraday for the circuit will be, well, it's going to have to be proportional to how fast the current is changing, and the proportionality is I'm going to just call something called self-inductance. Okay, so in this circuit, what's going to happen now? If you say A to B and back to A to back, so if you work it out, A of this, try to write Faraday law here, and this is coming from Faraday law. So either you can do it like this, go in the circuit like that. So these are like a DL. So you can do E dot DL, A back to A, equals to minus d dt B dot n hat dA. So if you do this, then this part is on the right side, on the left side is this part on the left side, and this is going to be minus IR, and this is just going to be L di dt. So it's L di dt, and so it's anytime t, so it's going to be this equation, and you can see I at t equals to I at 0 e to the minus RT over L, RT over L, because L can go down here, and so T has a unit of L over R. So this is a dimensionless. So sometimes people memorize this for the decaying circuit, and so if you memorize, that's fine, and you can use it to solve these kind of problems. So this one is Imax. Imax is V over R. So this is V over R e to the minus RT over L. Let me erase this and then try to give the numerical value for that. Okay, so I have it here. V is equal to 100 and R equal to 1000. L equals to, this is really humongous, this is 30 Henry. So okay, now we got all of this out of the way. So this I max equals to V over R. So let me just get the value of I max. That's 0.1 amp. So I max times math.exp. Okay, I have a let's see, it's going to so we haven't really solved this. It's a 10% value at t equal to 0. So we need to solve 10% of I got ahead of myself there using calculator. Okay, so we want to solve this equation, this thing here. You want to solve by 0. It's a to reach. So 1t when I equals to 0.I max. That's what we want, right? So in this equation, we just do 0.1 I max equals to I max e to the minus R over L. R over LT. So of course I max cancelled out from both sides, and take a log. So log 0.1 equals to minus R over LT. So this is minus log 10 equals minus R over LT. So T equals to, and this is natural log, L over R log 10. So we can find out what L over R is multiplied by log 10. Okay, now I got it. That was a little bit of quick. Let's see. So we have, say, tau equals to L over R, and let me just say log 10. Is it get natural log or not? No. So I have math.log 10. It is natural log. Okay, so I need tau start math.log 10, and that's many seconds, 0.069 seconds. It takes a while. So 0.069 seconds or 69 milliseconds. Okay, so that's the B. Okay, so we got B. How do you do C? How much energy is dissipated in that time? Well, let's look at the circuit. You have a circuit. This is the circuit that we're talking about, and this is the place that the energy will be dissipated. So at some time you have a I of t, and I of t is given as I max, or I max 1 minus e to the minus r t over L. No, not 1 minus. That was charging, and this is discharging. So you can see the formulas look similar, but they are very different, right? I mean, this is for discharging. So we have a discharging circuit. So at t equal to 0, it's I max. At t goes to infinity, it goes to 0. So this is the one we had on an earlier slide. Okay, so this is the only place the energy dissipates. So you might remember that power is the rate at which energy is getting dissipated. Power equals to I square R, right? I square T, or you can just say I T times how much the voltage drop across the resistor. So and this is the same, and so if I put that in there, that's equal to I max square e to the power minus RT over L, 2 times RT over L, if I square that. Okay, and so I am looking at from t equal to 0 to t equals to this 0.069069 seconds. So this is, I need to, if you think of this as dE dt, then basically it's an integral, right? So dE equals to I max square e to the minus 2 RT over L dt, and it's going to be 0 to this time. Let's call it big T. And so this is the delta E. When you integrate this, what's going to be I max square, and there is R here that I forgot. There's R here, I max square R, and 2 and then 2 this is going to be L over 2R and e to the power minus 2RT over L and 0 to T. When it's 0, it's 1. When it's T, it's T, and this minus I can absorb it here. So this will be RI max square, and this R cancels out. So this is L times L times R max square over 2 e to the minus 2R, this T, this is the T over L. So that's the value I need to figure out numerically. Okay, let me do that numerical. Okay, so I typed this in my little Python script, so I can easily do it. And so this is 0.0015 joules, so 1.5 millijoules. So this is just a 1.5 millijoules. So that's the answer for that. Okay, I think this is a pretty instructive problem. There are a lot of little details here and there that are in this problem, and I went over it pretty fast. So if you want to go ahead and kind of redo it or something like that on your own, you may try to do it. I want to address another question that just comes up quite often. Like, when you have a very large inductance circuit, self-inductance circuit, then you really need to let the current die out. So suppose I had a switch. This switch was not letting the current go this way. It just say the switch went like that, and it was just dangling out there. And so this was like that. So if you said that I'm going to just have no, and it's going to go this way, I'm gonna have a switch. I'm gonna have a switch just goes this way to nowhere, unconnected, connected. Then the current Imax, you can see it was Imax was going through this and going no place to go. It comes here and then just there's no place to go. So it can jump over here. So there will be huge electric field. This would be like a path through which electron can jump, and so this field flux through this. Flux through this area will be changing because our current is still flowing and is changing, current changing. And so you will see a spark, and can be pretty dangerous actually when you open the circuit like that. So this can be a dangerous, so this will be dangerous, a spark, and can cause big injury. That's why whenever you have a high inductance circuit, you would want to have a alternative path for current to actually end up decaying in this manner. If you plot this, the decay of the current is simply some Imax, and it just decays like that. And that depends on the R and L values, how fast it decays, but it decays smoothly rather than suddenly go to zero. Okay, and it allows for a smooth transition. So whenever you have a high inductance circuit, you want to make sure that you give a path. You use switch, which is of this kind, and not this kind. This kind switch is bad. You want switch of this kind. okay, and which has a path that bypasses the source, but actually lets the current to flow and die out slowly. Okay, this is probably where I will stop. I just want to remind you that if you haven't subscribed, I'll appreciate if you can subscribe to this channel. If you like this kind of explanation, please hit the like button. You can get more of this at my website here that has a almost the entire textbook free of charge. Okay, take care and bye.